have any announcements today? No? Okay. Okay. So it's a pleasure to welcome here today as our colloquium speaker, Dr. Enrichetta Iodice. She did her PhD in Trieste, and after that, she went back to Naples. She's from Naples to do first a postdoc, and then since then she's been a staff astronomer there at the Observatory of Capodimonte. So she's an expert in the field of extragalactic astronomy. In particular, she's an expert in the loss of brightness universe. Which is the lowest densities of stars of objects of the low that have the lowest densities of stars. When I first met Enrica, she was the PI of two of the most deepest, amazing, and successful surveys with the very, very large telescope, the Very Large Survey Telescope, which are the Fornax Deep Survey, which are very deep images of the Fornax cluster of galaxies, and the Very Large Survey, which are targeting early type galaxies. Now, we lost her to the ultra-diffuse galaxies, which is what you're going to learn today, but I hope to soon bring her back to the diffuse light side of the loss of brightness universe. So, thank you very much, Enrica, for coming here, and we'll have whenever you can.
Thank you very much for inviting me, and it's really a pleasure for me to be here in your fantastic institute. Just arrived on yesterday, never been here before, and I'm enjoying the environment. And today I'm going to present the results from an ESO Large Programme named LEVIS, Italian pronouns. And LEVIS stands for looking into the faintEst with MUSE. And the topic is just the structure and formation of ultra-diffuse galaxies, which is one of the most diffuse galaxies known, fainter galaxies known in the universe. And so the topic is just exploring the low surface brightness universe from the spectroscopic point of view. As mentioned, okay, that's what. Okay. No. I have to stop sharing and resharing again. I missed my presentation. Again. Doesn't work. Oh. Okay, now what? Oh. Okay. So the LEVIS project is an ESO Large Programme. We got more than 130 hours with MUSE to study a complete sample of ultra-diffuse galaxies in a cluster environment. This is the first homogeneous integral field spectroscopy. Homogeneous, I mean previous study to target single or few objects in different environments. But a complete sample in one environment like a cluster was never studied before. So this is the outline of this talk. So first of all, I would like to set the scene and just say why we are interested in studying low surface brightness galaxies. And I would like to mention a bit which is the state of the art of the studies regarding ultra-diffuse galaxies, and then go into the core of this talk, presenting the targets, so the Hydra I cluster, and the results from LEVIS. And I would like to conclude also to give you an idea what we are still missing for this topic of research. Probably most of you know that the main scenario for formation of a structure in the universe is based on the lambda CDM paradigm, where we expect that structures are still growing in the universe. In this process of mass assembly, some relics are still detectable in the clusters. The relics are, also the ultra-diffuse, the intra-cluster light, tidal streams, merging remnants, which are the main feature resulting from the gravitational interactions between galaxies. In addition, in the outskirts of galaxies, satellite dwarf galaxies are still accreted. And based on this paradigm, we expect that there is an observational counterpart of low mass dark matter halos. And so this is the theoretical point of view, and this is the observational point of view. I mean that we are still missing the optical counterpart of many of these many low mass dark matter halos that we are still missing. So this is the reason why we are interested in detect and study the low surface brightness galaxies, the faint end of the luminosity function. So this is the concept. So which kind of galaxies are ultra-diffuse galaxies? Ultra-diffuse galaxies are something like this one. This is they appear on the scene more than 20 years ago, introduced by Van Dockum, even if low surface brightness galaxies were already known since 18th. And Van Dockum named this kind of very diffuse object like ultra-diffuse galaxies, where a huge number of these kind of objects were discovered from Van Dockum in the Coma cluster, and they are empirically defined to be very faint, with the central surface brightness of 24 magnitude per arcsecond square in the G band, and have a size, and for size I mean effective radius, larger than 1.5 kiloparsec. Looking in the plane of scale versus stellar mass, UDGs are located here, and they have comparable stellar masses with dwarf galaxies, but they have a scale, and I mean scales as a half-life radius, which is comparable to bright late-type galaxies. So, looking in a larger context, I mean comparing ultra-diffuse galaxies with the dwarf galaxies, since physically we do not expect such a gap in the main structural parameters between dwarf galaxies and UDG galaxies. In this excellent work done by Lim and collaborator on the population of dwarf galaxies and UDGs in the Virgo cluster, we can see that the UDGs populated the extreme trends in scale, radius, surface brightness values. And in particular, if we look at the luminosity and effective radius, they are the outliers of the distribution. So studying ultra-diffuse galaxies, we are really mapping the faint end of the luminosity function and also the largest and faint galaxies known. With the new observing facilities, both in particular from deep imaging surveys, we were able to collect a lot of new results for ultra-diffuse galaxies. In particular, if we look at the colors of ultra-diffuse galaxies, it appears that we have two kinds of population. We have red ultra-diffuse galaxies, more located in the densest regions of the cluster, but bluer objects are also found, and they are located in the outskirts. About kinematics, since they are really faint objects, the stellar kinematic is quite hard to obtain. However, there are few data that suggest that these galaxies have a low velocity dispersion, and this is something expecting given their low luminosity. And few data suggested that they do not rotate. About stellar populations, like colors, we have UDGs that are on average quenched and cold, but the few objects which show star-forming regions are also found. Globular cluster, like dwarfs, UDGs also host a number of globular clusters that are expected based on their total luminosity. There are some UDGs in comas seems to have a higher specific frequency, so a larger number of globular clusters compared to their total luminosity. And finally, the dark matter content, which is one of the most debated issues for ultra-diffuse galaxies, since given their low luminosity, they should host a massive dark matter halo to survive into to the cluster tides, especially in the core of the cluster. Given that, dark matter dominated UDGs are indeed found, but looking at the statistics, there are also UDGs which have a normal dwarf-like dark matter content, and in some cases, there are also UDGs with no dark matter content. You can realize that to be consistent with all these really different observations, we cannot imagine that a single formation channel can exist. So we have a different kind of formations for UDGs, and I have tried to summarize them right now. Also, not only I would like to mention the mechanism, but also which are the observational properties that we expect for this kind of formation channel. First of all, as also suggested by Van Dockum, ultra-diffuse galaxies can form from a high surface brightness galaxies where heat lost the gas supply at an early end. So there is no more fuel to support the future star formations, and so they are named as veiled galaxies. These kind of UDGs are expected to be red, quenched, metal poor, and also host and they should also be dark matter dominated, and they should not host gas because they lost the gas supply. Recently, the formation of UDGs is also reconducted to dwarf galaxies, so they might result as puffed up dwarfs for different kind of mechanisms. Internal mechanisms where, for example, strong star formation feedback, for example, from supernova explosion, can just push away the gas in the central regions, or, for example, high-spin dark matter halo, so that, again, pushed gas away. And in these cases, UDG are expected to still host some gas in the outskirts and have a dwarf-like dark matter halo. External processes might reconcile with interactions between galaxies, in particular between a dwarf-like object with massive galaxies. In this case, we expected that UDGs are more gas poor, have a dark matter and metallicity that are function of the environment. This is not the full story because like tidal dwarf galaxies, I mean dwarf galaxies that forms from the tidal tails of emerging galaxies, UDGs might form in the same way. And it has been suggested that UDGs might also form from the collapse of the gas clumps in the jellyfish galaxy. In this case, we have there are observations for UDGs system, but this is to date there are no UDGs found in the jellyfish galaxies. In these scenarios, UDGs should be dark matter free, should be bluer and metal richer, and might have gas and UV emissions. So, putting together all these channels, we can anyway we can explain, be consistent with the observations, the wide range of observation and parameters observed for UDGs. Recently, there is a nice work done by Luisa Buzzo. She's a PhD student in Australia, where she tried to collect many data from UDGs, different clusters, and she had a multifaceted approach. So she looked at the imaging properties, spectroscopic properties, and she ended up with different properties for UDGs that results from puffed up dwarfs, which has a lower stellar masses, different shape. They are younger in age, differently from the failed galaxies, which on average have, for example, they are younger and they are more regular in shape. The star formation history also was is different. In particular, they are it stopped before than the puffed up dwarfs. So this work suggested that to discriminate between the different formation scenarios, we really need to take into account the different properties. So how we can get the observables to study the UDGs formations? For sure, we need the deep imaging. Deep images not only because we need to detect the UDGs, but also to study the shape, to study the colors, and the morphologies, and also to have a selection of globular clusters. However, the discriminant point is the spectroscopy, because thanks to the spectroscopy, we can address, we can constrain the stellar population, we can constrain the kinematics, and as a consequence, also the dark matter content. And the first integral field spectroscopic data with MUSE were just derived for the Dragonfly 2 ultra-diffuse galaxies done by Emsel and collaborators, and results suggest they were able to identify and confirm the point sources and globular cluster and some planetary nebula too, and they end up with the suggestion that these UDGs do not rotate. Now we have LEVIS. With LEVIS, we are mapping more than 30 UDGs in Hydra, in the Hydra I clusters, and with MUSE. So we have also the spatial information for stellar kinematics, so that we can study the dynamical mass, the dark matter content. We can address the stellar population, and also study the globular cluster system. For all UDGs in Hydra, we already selected globular cluster candidates using the deep images that we have. And so with LEVIS, we can spectroscopically confirm and estimate the spectroscopic specific frequency, which is strictly related to the halo shape too. So we have an independent measurement of the dark matter content. So what about the target? This is the Hydra cluster. It is located in the south hemisphere. It is a quite massive cluster with a dynamical mass larger than 10 to 14 solar masses. And it is located at more 50 megaparsec per mass. This is the core of the cluster. And if we look at the density, spatial density of the galaxies, we see that the highest region, as expected, is the core, but there are two other subgroups in the north and in the south. There are a few pictures. The core, this is the core of Hydra, and in the group in the north, we detected a huge amount of intracluster light and also many features related to ongoing interactions. The group in the south is, yes, in the southeast is completely different. This is a foreground group that is merging into the core. And we are mapping the harassment process in particular that are there are jellyfish galaxies, run pressure strip ongoing, run pressure stripping there. So this is a really nice environment to try to map the different kinds of formation mechanisms for UDGs. These are the Hydra hosts a huge number of dwarf galaxies, so we have also the chance to compare the structure of UDGs with the parent dwarf galaxy populations. And in Hydra, we detected 24 UDGs plus 6 low surface brightness galaxies, which are intermediate between dwarf galaxies and UDGs. This is the Lewis sample, and just to give you an idea, since these objects are really faint, to reach a minimum signal to noise of 10, which is absolutely important to derive a reliable stellar kinematics and stellar population, we need to exposure from 3 to 6 and more integration time on time. Given that, just to give you an idea of the kind of UDGs that we are in Hydra and convince you that we can really map the different kind of formation channels. This is the plane connecting the central surface brightness with the effective radius. These are the regions where dwarfs are, low surface brightness dwarfs, and extended dwarfs. This is a typical ultra-diffuse galaxies in Hydra, but we have also kind of extended and higher luminosity dwarfs, and the main I think interesting objects are those in the transition regions between ultra-diffuse galaxies and dwarfs, because we see tidal distorted systems that probably are just transforming from a dwarf galaxy to in a UDG. Given that, have a look at the Lewis result. This is the typical spectrum. This is the stacked spectrum inside the one array for one of the UDG in Hydra. And there are really few absorption lines. In particular, we can map the H beta, the H alpha, and if we are lucky, also the calcium triplet in the near infrared region of the spectrum. And so, start from stellar kinematics. This is the work done by a postdoc in Naples, Chiara Butita. And the first question was, since we can have the two-dimensional map of the velocity of stars, the first question was, the UDG rotate? And we have some cases where this is the 2D maps in the Voronoi binding map along the major and the minor axis. And here we don't see any appreciable gradients. However, there are UDGs like this one, where on the other end, we can measure some kind of velocity gradients along the major axis. What about the full sample? We have at least half of the sample, which shows a gradient along the major axis. So The rotation is not an exception, but in our sample, we have UDGs showing stellar rotations and UDGs that just are pressure dominated, pressure supported. Comparing the rotating UDGs with the dwarf galaxies in the plane showing the ellipticity versus angular momentum, we see that they are consistent with sample of dwarfs studied using, these are from the SAMI survey, and they have comparable value. What about if we're looking at the scaling relation like the Fabre-Jackson? We see that most of the UDGs in Lewis are consistent with the dwarf-like Fabre-Jackson relation. However, we have a couple of points which where the rotation velocity is comparable to the velocity dispersions. And in these regions are located galaxies that they are really rotation supported. What about the dark matter content? This is the comparison of the dark matter content between UDGs in Hydra with dwarf galaxies in the local group. And we have that on average, the Lewis sample are more dark matter dominated compared to the dwarf galaxies of similar total luminosity. What about the stellar population? This is the subject of a PhD student in Naples, Goran Dol, who explored the stellar population for the whole sample. Here is the plot between stellar metallicity versus age compared to the literature sample of UDG. And we see some kind of bimodality also in metallicity. In particular, we can say that on average, UDGs are cold and metal poor, comparable with the already known UDGs metallicities. However, there are some UDGs which show higher metallicity value. This is looking at the phase space. We see that the UDGs with higher metallicity are mainly located in the early infall region of the phase space, while lower metallicity galaxies are in the late infall. So there is some kind of in trend with the environment, shaping the galaxy structure and in particular the metallicity. This is something also expected because this is what we also see for normal high surface brightness galaxies. If we look at the mass metallicity relation, here there are the mass metallicity relation for dwarf galaxies, bright galaxies, and high redshift galaxies. This is the location of UDGs that are in the late infall regions and UDGs in the early infall region of the cluster. And you see that, on average, they are consistent with the mass metallicity relation for dwarf galaxies, except I would say half of the sample that show larger metallicity. With respect to the literature data, we do not measure lower metallicity as other UDGs shows, which would reconcile with the failed formation scenarios, for example. Looking at the star formation history, we realize that looking at the alpha enhancement, the galaxies in the early infall region formed very quickly and in an early epoch. On the other hand, in the late infall, we have a more extended or delayed star formation history. So there is a segregation in the metallicity and star formation history of the UDGs in Hydra. So from the stellar kinematics and also from stellar population, we have at least two kinds of population of UDGs. And so the question from the stellar kinematics, we have rotation supported and pressure supported UDGs. From stellar population, we have metal poor, meta-rich that are located in different regions of the cluster, and they have prolonged or fast star formation history. So the question is, are these populations related to each other, or they are simply, or they are disconnected? So I did this exercise. We use the faintEst because this is the tool to discriminate where the galaxies are located with respect to the environment. And if we look at the UDGs with rotation, you see that they are distributed everywhere in the cluster. So we don't see any distinction. If we look at the pressure-supported UDGs, we see that most of them are located close to the cluster core. If we look at the metallicity versus the dark matter content, the dark matter dominated UDGs are mainly located in the early infall region of the cluster. On the other hand, the dwarf-like dark matter content are distributed in any position in the phase space. If we compare the star formation history versus kinematics, we see that galaxies with rotation have on average prolonged star formation, but they are distributed everywhere in the cluster. On the other hand, the pressure-supported UDGs have a fast star formation history and are located in the early info. So, putting together all this information, what we realized? We realized that in the late infall region of the cluster, so the galaxies that are still joining the cluster potential, we see that we have UDGs that have rotations, have a dwarf-like dark matter content, have an extended star formation history, and the metallicity is consistent with the typical metallicity for dwarf galaxies. In the early infall, we have something mixed because we find galaxies with rotation, but also pressure-supported systems. The dark matter content is something on a larger range. So we have a dark matter dominated object and dwarf-like dark matter galaxy. On average, the star formation history was fast, and the metallicity is also, we have galaxies that are consistent with the typical metallicity for dwarf, and also have objects with higher metallicity. So we can for sure say that in the early infall regions, we have two kinds of population, just to reconcile with these mixed observations. On the other hand, in the late infall region, we can say that we have a single population of UDGs because all of them have same kind of properties. So to reconcile with this kind of observations, they reconciled with the puffed up scenario. On the other hand, in particular for UDGs that show high metallicity, as also suggested in the literature, probably some tidal interactions with the environment triggered was responsible for observing a high metallicity because there was probably part of the galaxies that are completely destroyed. So the high metal-rich part of the galaxy remains. So what about the globular cluster, which might add more on to these pictures? The globular cluster stuff is the subject of the PhD thesis of Marco Mirabile, who is a PhD student at the Gran Sasso Institute for Physics and Astrophysics. And in Hydra, a bunch of UDGs show globular cluster like in this picture. So the first thing is to establish really we need to confirm spectroscopically the globular clusters detected in Hydra. And so we can derive the specific frequency. And therefore, Marco also used the imaging, deep images to be combined with the MUSE data and have a better, and so that it can improve the detection of the globular cluster. So these are preliminary results that Marco is going to publish. And these are the globular cluster numbers and specific frequency for some for the 4 UDGs already studied by Marco. And you see, compared to other UDGs in other clusters and also dwarf, we see that on average the specific frequency is consistent with a larger content of globular clusters in UDGs, like observed in COMA and sometimes also in Perseus clusters. However, we have one case is where the detection of UDGs of globular clusters is quite uncertain. Looking at the dynamical mass, the values are consistent with the total dynamical mass estimated from stellar kinematics, and they confirms that these galaxies are dark matter dominated. Finally, I would like to show you 2 special cases that we also have detected in Hydra. First of all, the UDG6, because the spectrum of UDG6 shows emission line. So the question was, is this galaxy star forming? This is the deep image where that shows the galaxies is not so regular in shape. And this is the MUSE white image. And this is the spectrum where you see the H beta and the O3 lines in emission, H alpha and S2 in emission. This is the subject of a thesis of another student in Naples, Luca Rossi. And if we look at the different emissions we detected, this is the distribution of H alpha, distribution of H beta, and the distribution of O3. So they are really diffuse they are really found covering the whole body of the galaxy. Looking at the OPT diagram, this is consistent with being a star-forming UDGs. And if we look at the distribution of the H alpha, we can derive the gas kinematics, and it seems that there is a rotation in the H alpha. We cannot measure the stellar kinematics because the emission of the H alpha is just on top of the absorption of H alpha, same for H beta. So we cannot constrain the stellar kinematics, neither the stellar population yet. And then we look at another special cases. This is the UDG32. UDG32 is located in this region of the cluster. This is a system of 2 galaxies, NGC 3314A and B. The A galaxy is in front, which is the bluest one. There is a huge run pressure stripping going on, and we detected extended stellar filaments from the center of the galaxies through the southwest. And in this region of the filament located at roughly 50 kiloparsec from the center, there is this yellow spot here, which is a UDG. This is really faint and really extended. And so the question was, does these UDGs formed from the run pressure stripping clamps? So the first thing, this is the subject of a work done by Johanna. Johanna is a tenure track at Oulu University in Finland. This is a better contrast image of UDG32. So the first thing, which are the expected properties for UDG32 if it formed from the gas clamps? First of all, it should be co-spatial with the filaments. So are we sure that it is in front or behind? So we have to check the redshift. Secondly, it should have a younger age and a higher metallicity with respect to the other UDG of the cluster, because it formed from already pre-processed gas, and should be dark matter. So in principle, all these properties can be get from the MUSE LEVIS data. This is the image from MUSE, and unfortunately, we detected a huge extension of H-alpha filaments, which are connected to the round pressure stripping that is ongoing in this galaxy. So, and the H-alpha filaments are just on top of the galaxy. So we were forced to stack the spectrum in a tiny region of the cluster. Here there are two globular clusters, and our second investigation is also to check if they are bounded to the galaxies or not. Because if they are bounded, we can exclude it that it is formed from round pressure stripping. This is the spectrum, so we can measure the H-alpha, or better, we can measure the redshift from the H-alpha. This is the redshift of 3314A. So try to answer the first question if the UDG is co-spatial with filament. This is the H1 associated to the galaxies from MIRCAT data. This is the redshift of the H-alpha filament that we detected from MUSE, and this is the redshift for UDG32. So indeed, the UDG32 is there in space. And these are the redshifts of the two globular clusters, so they are mainly intracluster globular clusters. So they are not bounded to the UDG32. What about age and metallicity? Since we cannot constrain age and metallicity from MUSE data because of the issue of the H-alpha filaments, we collected DECAM data. And we found, using a SED fitting, that the UDG32 has a younger age and higher metallicity with respect to the other UDGs in Hydra. So it also seems that we are on the right way. Unfortunately, we cannot constrain dark matter content here because we are not able to constrain the velocity dispersion from the teeny H-alpha absorption. So follow-up studies would really need to finish the puzzle, to complete the puzzle. So just to summarize, the Hydra I cluster and the MUSE observations for the UDGs in Hydra I cluster can really provide a complete picture of the formation channels for UDGs, because we were able to explore different properties, and also the different locations in the clusters can provide some confirmation or not of the different formation channels. We have found that half of UDGs show rotation, and this is one of the most important results from LEVIS, because to date, most of the dark matter estimates were based on the velocity dispersion from the long slit spectrum. So, in principle, if you don't know if rotation is present in the galaxies, your velocity dispersion has a bias. And as a consequence, you have an unconstrained dark matter content. So since now we know that UDGs can rotate, as also some dwarf galaxies do, we should be able to account for the rotation when we estimate the dark matter content. They are dark matter dominated, and this is something that we already knew, that we already known from previous observations, that age and metallicity are consistent with the typical values for dwarf galaxies. And there is a gradient in the stellar population properties that reconcile with the location inside the cluster. So there is this kind of trend. So we have a single population in the late infall regions, so we can explain their properties with a single formation scenario. On the other hand, looking at the high density region of the cluster, there are at least two kinds of populations. Plus, we have some other peculiar, would say, galaxies that show star formation, ongoing star formation, and UDG 32 might be the first discovered UDGs formed in the rapprochement stripping filament. What about future? Here there is a picture, try to summarize what we have and what we miss. What we have, thanks to the deep imaging survey collected in the past decades, we have a huge statistics on the globular cluster's main photometric properties, I would say. The kinematics, a lot is to be done. So the statistic to measure the metallicity, age, and velocity dispersions is, we have data, but just to give you numbers, we have more than 3,000 UDGs discovered, and the kinematics is available for 100. So we have an order of magnitude between the photometry and the stellar kinema. And what we really miss is all the remaining properties. We should improve the statistic for searching for gas content, which is one of the discriminant characteristics between the several formation scenarios. We still miss measurement for the stellar rotation, and we still miss the properties of UDGs at higher redshift. So with the next observing facilities, starting from including Euclid that it's running now, but Rubin LSST and ELT in the future, we can really gain more on this topic. Done.
Thank you very much. Thank you very much, Enrichetta. Questions? Come on. Don't be shy.
Maybe I'm not I wonder if is the stellar kinematics the only method to constrain the dark matter content? There is another method.
No, we have you can constrain the dark matter content also from globular clusters, because the specific frequency is related to the dark matter halo in the dwarf galaxies in general, but it seems that the relation is still valid in the low surface brightness regime. So these are at least the two, stellar kinematics is something important because you have the velocity dispersion, or better, the line of sight velocity distribution. And right now, they focused on the velocity dispersion because you have a long slit spectra, so you do not have the information, the spatial information. And even if you think to put your long slit along the one axis of the galaxy, since the UDGs are quite irregular, roundish, you do not know really where is the major axis of rotation. So you can put your slit in another direction, and you didn't you are not able to measure the redshift. No? If you can also mapping the velocity dispersion and rotation velocity along the radius. So usually they take the stacked spectrum. Yeah.
Because the UDGs has a rotation,
Mm-hmm.
then they are more likely to be the cells.
Yes, Oh, okay. In principle, no, because you can have rotation. You have dwarfs that rotating and high surface brightness galaxies that might rotate. So this is not a discrimination between the two kind of channels. But there is this is important for the dark matter content of the galaxy. So for sure, we can say that if there is an external tidal interaction, this might destroy completely the ordered motion. So you can indeed think that the galaxies that do not show rotations are and have high metallicity might reconcile with an external processes in their formation history. So from this point of view, yes, but not in principle.
Correct me if I'm wrong, but it seems to me that all this work and the possible formation scenarios have been extracted from galaxy clusters, right? But have you considered or searched for populations of UDGs that are not in clusters or not related to clusters at all?
This is a nice question. Thanks, because let me to clarify. So we have two problems, okay? The detection of UDGs was focused on clusters because clusters are best studied environment with the imaging surveys. So there is a bias in the selection, okay? We have some measurements of structural properties based on the images for the Hubble frontier fields, where we detected a gradient in the colors between UDGs from the core to the outskirts. And why we can map the outskirts? Because frontier field clusters can have an angular
Coverage?
yes, coverage. Sorry, that stayed in the field of view of Hubble Space Telescope. So close by clusters, you need a huge number of pointings to cover at least the virial radius. For example, for the Virgo cluster, you would need more than 101 square degree pointing to cover the whole extension of the high density regions of the cluster. So you would need at least the same number of pointings to cover the outskirts and so the filament. So you are correct. We would need to map the low density regions of the clusters to map the properties of UDGs in this region. But we still miss because of the coverage, at least for nearby clusters. And in this sense, for example, Rubin LSST with such a wide coverage could improve a lot.
How will you define the UDG with the mass around 10? So I just wondered, is that possible we have like a something like UDG?
So that range of masses, I think that it still need to be explored. No, to my mind, looking at the stellar mass metallicity relation, we are 10 to the 7 as the lowest values that we get, but not 10 to the 6.
The thing is that when you go to lower and lower masses, this becomes way more complicated because it's fainter and fainter. So imagine
fainter and fainter, and if you do not have a massive dark matter halo, they are not stable. On average, the stability of UDGs from simulation is about few gigayears. If I remember well, 3-4 gigayears from the Cinzio simulation. So they are not long-lived systems, except if they have a huge dark matter content. So they are unstable.
I have a question. So how do you reconcile what you find with what Luisa Bujo said? Because she finds that lower metallicity are the early infos, right? The ones that are failed. But you find the kind of the highest metallicity are the more like.
Okay, the low metallicity are in the late infall region.
Yes.
The high metallicity are close into the close to the early infall.
Yes.
But there is one important point. In Hydra, we are mapping only 0.4 of the virial waves.
Okay.
So to be honest, I would not say that the late infall is really the outskirts of the cluster. And the galaxies studied by Luisa Buzo are really in a more empty regions, like loose groups, for example. In fact, she found a really lower metallicity, which reconcile with the high redshift mass metallicity relation. And so, in the end, in Hydra, I think that given the metallicity, we can exclude that we have any failed galaxies. So I would say that all UDGs are results from puffed up dwarfs, but with different mechanisms, internal or tidal interaction. So this is the main conclusion that came into my mind, putting together all these pieces.
Okay. Well, if not, let's thank Enrica again. Thanks a lot. Thank you very much. Sorry that there were like not many people.